In this segment, we'll put together some of these ideas to obtain the minimum uncertainty wave packet. And I first should explain what that is. And what we'd like to find is the wave packet for a free particle that has the minimum uncertainty, and minimum in the sense that this product of the uncertainty in the momentum times the uncertainty in the position is the smallest it can possibly be. And pretty obviously the smallest it can be is when we get equality. And when you have this condition hold, then one says one has, for whatever that quantum state is, that one is in a minimum uncertainty state. And we don't know when does this apply and when can we achieve that. Yeah. Well, if you go back and look at our proof of the generalized uncertainty principle, we used inequalities in only two places. The rest of the time we were doing things that were all equalities, everything being equal. We used it first in the Schwarz inequality and got an approximation there. Not an approximation, but a bound. And then we also used it toward the end when we used this property that for any complex number, the modulus squared of the complex number, which is just the real part squared plus the imaginary part squared, is always greater than if I just took one of those. So A is the real part. If it's which obviously it's either 0 or a positive number, and if I drop that off, then whatever's over here, all positive, is going to be greater than just just this one part. You know, the whole is greater than the sum of the parts, and then the imaginary part we wrote like this, and did some manipulations from that point on. So if you go back and take a look at your notes on that, then the first of these occurred when we made the step like this. We'd manipulated things into this form: the uncertainty in A, well, the standard deviation squared in A, and the standard times the standard deviation squared in B. We'd gotten into a form that looked like this: inner product of F with itself, inner product of G with itself, and that we then use the Schwarz inequality to make that this is always greater than or equal to this quantity squared, the inner product of F and G squared, or absolute magnitude squared. So the question is, when does that inequality hold? And I would claim it's fairly obvious, should be fairly obvious, that the inequality holds, or the equality holds, the equal sign holds in this picture, when G is some complex number times F. It's just linearly, is linearly dependent on F. They're not linearly independent vectors. C can be any complex number. And then really you can show it that equality occurs then simply by doing direct calculation. So I want to calculate this side over here. So F inner product with itself, G inner product with itself, and then use this assumption, CF. And if you look at that, that becomes FF, CF, C star F when it comes over here. And you pull the C's and C stars out, and you get the absolute modulus of C, a C here and a C star when you pull it out here. And the net effect is that you have F and F inner producted with itself, and the absolute modulus of C squared. So that's the if you like, that's this side over here. And I can calculate this side in a similar fashion. Again, it's just this product complex conjugate times itself. Again, you can pull out the stars and pull out the C. This becomes C squared, and you get F squared, F squared. And if you compare this one and this one, they're obviously equal. So what we can say is that when G is some a complex constant times F here that the equality holds up here. Yeah. So that's when the equality holds in the Schwarz condition, Schwarz inequality. The second one occurred, if you remember, we had this, you can go back and look in your notes, but we had this expression, absolute modulus squared, and this is just a complex number, and so we could write it as a real part of whatever that complex number is, squared, plus the imaginary part squared. That's just exactly what we did here. Complex number, real part squared, imaginary part squared, equality. And then once you look at that, it's not too hard to see here. When does equality hold? When is this thing equal to this one? Or when what we did was we dropped this one here. Yeah? Here. And so a positive number squared and the positive number squared, well, they always, the sum of these two positives has to be greater than just one of them squared. But what that means is when the equality holds is when the real part is equal to 0. So this inequality that we used, the equal portion of it is the very special case where F and G are orthogonal to one another. Their inner product vanishes. At least I should say, when the real part of their inner product vanishes. So if that occurs, then you get equality. But I know that G is C times F, where C is some complex number. I can pull this out, and the F, this is just the absolute modulus of F squared. So for any state vector, that's always a real number. And so if that's real, and this is a complex number, and I want the real part of this to be 0, that says that this complex number has to have only a real part. This is real. This in general might have real and complex, but if its real part of this whole thing vanishes, then C can only be a complex number, a pure imaginary number, I should say. So C is pure imaginary. And when those two things happen, then we get equality. That the standard deviation of A times the standard deviation of B is equal to H bar. Now, here it's sort of traditional to use, instead of C being a complex, explicitly write that it has no real part. It's just I, imaginary number, times a real number A. And then if you go back and take a look at things, F was this vector. That's the way we defined it. And G was this vector, the operator operating on the state function. And now then, if I have G is equal to I, F, then I have a relationship that I can solve, at least in the case for momentum and position. Well, that's of interest. So now I'm going to look at the case where the A operator is the position operator and the B operator is the momentum operator in the x direction. And this equation here then becomes B, which is momentum operator, minus the expectation value of momentum operator, psi, is equal to I times some constant, imaginary, that's our C that had to be imaginary, times F, and F, A is X, so that's the expectation value of X, times the wave function back again. So we get this equation here. As we've seen, if we look at the X components of these, this turns into, this momentum operator turns into H bar over I partial with respect to X. Now it's going to be a little easier for me to write this expectation value of P is just P bar. It's a number, and for us it's a real number since momentum is a real quantity. And so this is the operator operating on psi of x. And over here, IA, the operator is just x. And again, I'll use x bar for the average value of x, or the same thing as the expectation, just to emphasize these two are numbers. X bar and x are numbers. And again, there I just set the notation, really, just reduces a little bit of writing. And now I've got a differential equation that in principle one can solve. Well, you can solve it. And just expanding out, this will give me here. I'll just look at one variable, so that becomes an ordinary derivative, minus p bar psi. Over here, I a x psi, minus I x bar psi. So this is all numbers here. This is a variable x, that's a number, and psi is a function that we need to solve for this minimum uncertainty wave packet. Oh, then what did I do? Then I just solve for the derivative of psi, so that entails bringing this over to the other side. So I get a p bar psi, and then added to these terms, and then multiplying through by I and dividing by h. So I get I p bar h bar psi. When I multiply through by I times I is minus, so I get a over h bar x times psi. And again, when I multiply by I minus I, that'll be a plus, and I'll get a over h bar and x bar. I've got a psi in each term, but they're just functions, so I can divide both sides by that, and I get this characteristic form. And then over here, I just grouped it a little differently. I made this the leading order one. Remember, I divided out psi, so it's just minus a h bar x. And then these other two, I wrote this one first. Remember, I divided out psi, and wrote this one second. And then we've done this lots of times. That's just the logarithmic derivative. And so it's the same thing as the derivative of the log of psi. Using implicit differentiation, derivative of natural log, I'll get 1 over psi times the derivative of its argument to get back up here. So I get this derivative is equal to this. Now these two are constants. These two terms, there's no x's there. This is a constant, but I've got an x here, which is the integration variable. So I just integrate both sides and introduce an integration constant. The integral of the derivative of natural log is just the natural log of psi. Derivative here of x, I've got a constant here, but the derivative of x, the integral of x, or the antiderivative of x, is x squared over 2. So that term is where the 2 comes from, and I get an x squared here. And the integral of both of these with respect to x, well, they're constants, and so the antiderivative will just get an x here and an x here. And then, of course, I've done an indefinite integral on these, and so I need an integration constant to give the most general form. So C is an integration constant. And then, with a little bit of foresight, I can write that arbitrary constant in this form. I'll just take out this piece. So it's some constant, I don't really care what it is, because I'm going to just let C be this plus the natural log of another constant. And so this arbitrary constant here, I can always find an A that will, I can write C in terms of this natural log. So I'm just transferring the arbitrary constant here. And now I've got something that I can make heads and tails out of. I actually combine things. I've added this term judiciously, and that's this one here, minus x bar squared a over 2h bar. And then the other two terms I had from above. That's these two terms. And then the one that has p in it, I just left it by itself. So that's this I p bar over h bar x. And then, of course, so I incorporated this one in this piece here, and then I've got natural log of A. And then what did I do? Then I factored out the A over 2h bar. And when I do that with a minus sign, I'll just get x squared. I factored out a minus sign, so I get a minus here. And this one didn't have a 2 in the denominator, so I have to put one in up here to balance it. And I factored out the a, x bar, h bar, and a 2, so this just becomes 2. I don't factor out the x bar. I factor out the a, 2, h bar minus. So I get a 2 x bar x from this term. And then factoring out a over 2h bar, I just have x bar squared. So I think if you multiply this out, these two terms after multiplication are the same. And the reason I wrote it in that form was because this becomes a perfect square. So I get a minus a 2h bar, and this quantity is just x minus x bar squared plus these pieces. And now then I can I can exponentiate both sides. E to the natural log just gives me psi. E to this is the same as e to this, and e to this. And e to the natural log a just gives me a. E to the I p bar h bar x just gives me this term. And then this term gives me this exponential of minus a h bar x minus x bar squared. And then if you wanted to, you could put back in the time dependence. Remember, there's a time dependence, which is the I over ph bar x. And in any event, you finally get the Gaussian term here, spatial dependence. And so these minimum wave packets are traveling waves, could be going in either direction, depending on the situation. But their shape is this Gaussian shape, this bell-shaped curve for a Gaussian distribution. So minimum uncertainty wave functions, wave packets always have this Gaussian shape, and as sort of an envelope over the whole particle, the wave function for the particle, I should say.